This is Iris Miano, Math 50, lecture video number, I think this is the fourth one. Let's see. 1, 2, 3, 4. Yes, we are going to be covering sections 1.6 and 1.7. We will spend class time on Monday discussing these two sections. We can have the discussion on 1.7 spill over onto next Wednesday as well, in preparation for getting everything figured out before the exam that's happening not this coming Monday, but the Monday next. Okay, in any event, let's go ahead and get started talking about ratios and proportions. This is what we'll be discussing for section 1.6. Okay, so let's start with a definition. Ratio, a comparison of two quantities by division. A ratio of A to B is this, A to B. It often has this fraction representation. Sometimes you could have, given the context, a colon representation in which the first item mentioned, A, would go before the colon, B would go after the colon. Otherwise, it's a fraction representation in which the first thing mentioned is in the numerator and the next thing mentioned after the word 2 goes in the denominator. Okay? A unit ratio is a value which is the result of simplifying the division. Of the ratio, which is to say that you're thinking of a ratio as a fraction or as a division problem, which all fractions technically are. If we were to actually perform that division to get a real number quantity, like maybe a decimal representation would be a little bit more forthcoming, then that would be considered to be a unit ratio. Otherwise, it could be a fraction whose denominator is a 1, in which case there would be no simplification needed. Okay, great. Let's go ahead and write each of these as a ratio and as a unit ratio and interpret the unit ratio in a sentence. So let's go ahead and set up 250 miles to 5 hours. 250 miles to 5 hours. So this will be our ratio. Now if we want to put it into a unit ratio, we'll actually perform the division. And another thing you'll want to keep in mind that I don't have indicative or slated clearly in this definition right here, is that the unit ratio will have the units in numerator units per denominator units. So for this particular first example, it'd be miles per hour, and we'll just perform the division. So how many times does 5 divide into 250? Well, it happens to divide perfectly with no remainder. So you can, just reach for your calculator for this. I'm totally fine with that. And divide 5 into 250, and you should get 50 if I'm not mistaken. Indeed. So that means the unit ratio will be 50 miles per hour. And interpret the ratio in a sentence. I would say something to the effect of, the ratio, the speed was 50 miles per hour. Because when you refer to a a rate as a speed, a ratio as a speed. Technically it's a rate because the units in the numerator and denominator don't match, but you know, ratio could also loosely be used as well here. Okay, cool. So let's go ahead and talk about this second example in which we first set up the initial ratio in which we just plop the first thing mentioned in a numerator space, that's 9 inches, and the second thing mentioned just gets put in a denominator, 36 feet. Cool, cool, cool. All right, so then we want to actually divide or simplify this as much as we can. So the unit ratio. Let's actually divide it, and it'll be coming to us in the form of a decimal, if I'm not mistaken. So if I reduce this fraction, just focusing on the numbers and not the units at all, the 9 goes into the 36 exactly 4 times, 9 goes into itself once, so it'll be 1/4, 1 over 4, right? Also known as 0.25 as a decimal. And yeah, unit ratios, generally we convert those into decimals. It's just a little bit of a convention. So that'll be 0.25 inches per foot would be the appropriate units there. And as a sentence, I know a little bit generic, you could say something to the effect, there are 0.25 inches for every foot. And what would be the context that in which this would be useful? Maybe some sort of scaling with a map, or some sort of other kind of blueprint item. You know how you draw things on paper much smaller than they are in real life in order to come up with a plan for how you're going to build something. Yeah, that could be a context in which this would be somewhat relevant. Okay, moving on. Let's define what a proportion is. A proportion is the equating of two ratios or rates. A couple of things to remember about proportions is that the units must, that's supposed to be a U, match across the equal sign. Ooh, I spelled across wrong. You guys see that? I'm a terrible speller. Let's try that again. Cross. There we go. The equal sign. And if you have an unknown in a proportion, you can solve for that unknown by using the cross product. Solve proportions containing an unknown by using the cross product. Here we go. Let's tackle this example. We have Joanna made 2 of the 20 batches of cookies for the party. Find the proportion of Joanna's batches at the party. Okay, so so we can set up the initial ratio. She made 2 out of 20 batches, so 2 batches for every 20 batches. So equating that to an equivalent fraction here by just like reducing it, that's one way that we could show the proportion. Batch. So for every 1 batch that Joanna made, there were 10 batches of cookies at the cookie party, okay? So yeah, the proportion would therefore be of Joanna's batches. So Joanna made 1 out of every, sorry, just a moment, out of every 10 batches of cookies at the cookie party. Sounds like a party I want to go to. Right? Right. Great. Cool, cool, cool. So yeah, anytime you have two rates or ratios set equal to each other, they've got to be the same units on either side. You can use a proportion, the idea of a proportion, to reduce a fraction in order to get a more simplified idea of what the the ultimate ratio is there. Okay, moving on to this idea of percent. Now, the percent is a particular kind of a ratio. It's a ratio of a number to 100. And literally, the word percent means for every 100. Like if you break down the root words of per and cent, it literally means for every 100. Okay, so anyway, the ratio of a number to 100, let's say you have x, and you put it in a ratio with 100, then you could say that this is equal to x percent. You can use that symbol there. And I'll put also in this little area here that if we break down the word per, it means for every. And the word cent literally means 100. Cool. All right, let's go ahead and do some practice in which we change the decimals to percents, okay? So the trick here is to, and I have a little bit of space above the particular numbers in order for me to write the procedure here. You're basically going to move the decimal place 2 units to the right. And then literally slap on, I'll say affix, it's a little bit more high rent word, affix a percent symbol. It's literally those 2 steps. So I'm going to go ahead and with my pen go 2 steps over. So that turns this 0.34 or 34 hundredths into a 34 when I move the decimal over 2 spots and then I slap a percent symbol next to it. Literally, that is it. That is all you need to do. That is all you should do. Okay. This next example, you'll notice that there's more than 2 decimal places in the problem. Does that change the process that I need to undertake in order to convert this decimal into a percent? No, it does not. It might feel good to move the decimal place all the way over to the end, but that's not the procedure. You are to move the decimal place 2 units, only 2, which will have it right after the 2 but before the 4. So that'll turn the decimal of 0.024 into 2.4. Slap a percent symbol next to that, and you're good. Yes, percentages could be decimals. Percentages could also be fractions too, just to make things extra confusing. All right, let's move this decimal place over 2 spots. Whoa, this turned in the 2.17 into 217%. Is that okay? Can you consider more than 100% of something? Actually, yes, you can, which might seem a little counterintuitive, but yep. That just means you have more than one whole thing is one way you could think of it conceptually, okay? All right, now let's go the other direction and change these percents to the decimals. So now here the procedure is take off, you kind of just do the previous procedure but undo it and in the reverse order. So we're gonna take off the percent symbol, symbol and move the decimal place 2 units to the left. Okay, just basically undoing what we did before. Take it off, and here's the decimal place currently. It's just kind of after the 3 in the 43, and we'll move it 2 spots to the left, so that's its new position, turning this number into 0.43. It was originally 43%, but as a decimal, it's 0.43. Okay, let's do it 2 more times. And remember, even though it might feel good to move the decimal more places or fewer places or whatever in a different direction than what you should, just stick with the procedure that's being described here above, okay? Don't do any more, certainly don't do less. Okay, again, take off the percent symbol. The decimal place is currently in this position. Let's move it 2 spots. Yep. So if there's an empty little spot that you traveled, it kind of, I liken it to the grooves that you see in an egg carton, and if you see an empty egg carton, put an egg in it, or aka a 0. So that'll turn this 0.6% into 0.006, right? You see how there's 2 zeros in front of the 6, but after the decimal point that I just put down? Okay, so then that'll give you this particular decimal place as your converted value. Okay, one more time. Take off the percent symbol. Take the decimal place, here's its current position, and move it over 2 spots to the left. That'll give you a decimal value of 1.75. Okay, so hopefully that all made sense and felt good. Let me know if you have any questions in lecture about that, if you want some more examples. Now let's go ahead and use percents and proportions with some wordy problems. Your favorite, I'm sure. So let's dive into this first example. It says a new washing machine that sells for $880 with a sales tax of $8.25. What is the total price of the washing machine? Okay, so the total price, let's just call it P, is always going to be whatever value it sells for, which will be $880 in this case, and then we'll need to add 8.25% of that sale price, or the price that it's selling for. So how do you do that? Well, if you recall from our translation lecture earlier, the word of corresponds to multiplication. So what we need to do is write this as a decimal. So remember, take off the percent symbol, move the decimal place over 2 spots. So we're going to put a 0 right there. So it'll be 0.0825 is this percentage value as a decimal. So that's what we'll multiply our $880 by in a separate term in order to account for the sales tax. So that's a raised dot right here. Okay, so this right here, just to be clear, is the sales tax. And that's the price. So, but what you get rung up for, selling price, I guess that's what I want to call it, selling price, sure. Just to distinguish it from like what you actually pay for. I guess that's what what is the total price? Maybe we'll call it TP, not to be confused with toilet paper. Total price is the selling price plus the sales tax. So reach for your calculator, that's fine with me. I would type this part in first, 0.0825 plus 880, and then add that to another 880 in a second step. Times 880 equals 72, and I'll write some stuff down in the interim. Like for instance, if you multiply this, you should be getting 72.6, right? And then add that to your 880. and you get $952.52. Oops, let me go ahead and make that 2 look a little bit better. And 6/10, but remember, we're talking dollars and cents, and you need to put this in a full sentence to answer the question, what is the total price of the washing machine? So you could say the total price is $952.60. Always take your dollars and cents value out to 2 decimal places. It's got to go to the hundredth place. Okay, so hopefully we're feeling real good about that. Go ahead and box that up, my final answer. Okay, another example. There are 1,535 animals at a sanctuary. About 43% of the animals are birds. How many birds are there? Now it says about here, which is something we definitely want to take into account here. So we might be more or less approximating what's going on here. We're going to, since we're talking about numbers of birds, we're going to round to the nearest whole bird, okay? Which may be rounding up, which I feel like might be a little bit of a weird thing conceptually for some folks. Like if you have a calculation and there's a fraction of a bird, wouldn't you round down? Not necessarily. We want to just follow the rounding rules that we know to be true. If the decimal that we end up calculating ends up being 5 or larger in the ones place, right, then we're going to round to up, you know, in the whole number area. And if it's 4 or lower, we'll just keep it the way it is and make sure there's no decimal, because we don't want to be talking about fractions of birds. Okay, anyway, in any event, we're going to take 1,535, and we're going to multiply it by 0.43. Is everyone on board with that? Because that is the decimal representation of 43%. Cool. Get out your calculator again. Take 1,535 and multiply it by 0.43. And you should get 660.05. I'll make sure I put that entire number as the end of my calculation here, but as far as what value I represent in my final answer sentence, I'm just going to keep it as 660. And I can reuse this word about in my answer to indicate that it is an approximation. So I'll say there are about 660 birds in the sanctuary. Sanctuary, yeah, okay, I think I spelled that right. Cool. And box that up. Okay, I think this might be the last one in this set. Yep, last one for 1.6, and it's a 2-parter. Very cool. It asks us to rewrite the sentences. If the sentence contains a proportion, write it so it contains a percentage. If the sentence contains a percentage, write it so it contains a proportion. Okay, so let's look at part A. It says in 2016, 73% of the beverages Professor Louis Martinez drank was coffee. Okay, so this contains a percentage. What we're going to do is we're going to turn it into a proportion, which could be represented as a reduced fraction or a decimal. That's one thing that I didn't mention earlier, is that totally you could have your proportion represented as a decimal, and let's go ahead and practice that now. So we can say, as our modified sentence here, the proportion of beverages Professor Louis Martinez drank in 2016, that was coffee. 0.73. Cool. Or you could have 73 over 100. That would be perfectly fine as an alternative value to represent the proportion version of 73%. Now for part B, clearly you see the word proportion right away in the first part of the sentence. So we're going to convert part B's sentence into a percentage. But let's go ahead and read it together. The proportion of time Lauren spent on the computer in the last month was 0.45. So converting 0.45 to a percent is hopefully at this stage relatively easy for everybody. We're going to move the decimal place over 2 spots to the right and slap a percent symbol on the end of it, calling 0.45 45%. That's the equivalent. So I'll say Lauren spent 45% of her time last month on the computer. Great. And that concludes what I have to present for section 1.6. Let's go immediately over to 1.7, continue this discussion now on square roots. So we're going to get a bit algebraic up in here. And let's start off with the definition. So notice that we have b squared equals a, this first equation being presented to us in regard to the definition of a square root. So when you have this relationship, when you have some number a that can be rewritten as a squared number, b squared that is, then b is considered the square root of a. Oops, let's add notes here. And we'll change the color up to this beautiful teal color. Square root of a. And let's, in the midst of this definition, consider a specific value of 25. You may notice that 25 is a special number. It is a perfect square number. So that means that 25 can be rewritten as something squared, right? And what is that something, the base that it could be squared in order to, give us 25? Well, it would be 5. So then we would say, thus, 5 is the square root of 25. So it is definitely in your best interest to get to know perfect square numbers. You'll see them in this section a lot. They are, let's see, all of the perfect square numbers from 1 to 100 are as follows. Well, first there's 1 is a perfect square number because it can be rewritten as 1 squared, right? Again, actually 1 is super special in that regard. It can be rewritten as 1 cubed, 1 to the 5th power, 1 to the millionth power. It's always just going to be 1. The next perfect square number after 1 is 4. And then 9, because 4 is 2 squared, 9 is 3 squared. 16 is 4 squared, 25 is 5 squared, as you see in this particular example. 36 is 6 squared, 49 is 7 squared, 64 is 8 squared, 81 is 9 squared, and then, of course, there's 100, which is 10 squared. And of course, there's infinitely many perfect square numbers after that. What's 11 squared? Do we know that one? 121. 12 squared is 144. And then generally, you're not really expected to know very many perfect square numbers after that, but what do I recall? Yes, 13 squared is 169. 14 squared, you know what? I don't know that one off the top of my head, but calculator will tell me right away. 196. Yeah, I should remember that one because it's just the 9 and the 6 switched from the previous perfect square number of 169. 15 squared, I think, is 225. Yep, 225. 16 squared, 256. Yep, so, and that's just based on my familiarity with these perfect square numbers. They come up later on in your mathematical career from time to time. All right, moving on to the definition of a particular kind of square root, the principal square root, okay? So that is represented by this symbol right here. So I'm going to just fill in the blank, principal square root. That's meant to be put in the blank there, okay, where this symbol is called the square root symbol. Now, if the little area above this, I don't even know, check mark part of the symbol had a number in it, then it would be another type of root. So we'll talk about that as it comes up. I think there's a cube root problem in the handout that you're going to tackle in your small groups. So have fun with that. I'm just going to go ahead and see what people can surmise that, how that is defined. I'll let you guys talk about it. And of course, if you have questions, I'll cover it with you at that point. I just want to give you guys a chance to look at it yourselves or in your small groups. And also note that if A is negative, A is the value inside of the radical in this particular formulation. So it cannot be negative. It's got to be positive. But if it is negative, then the square root of A is imaginary or not real, we'll say. All right, and we are dealing with only real numbers in this course. We do not dive into that imaginary world. There's a whole nother number set disjoint from the real number set, and it's the imaginary ones. Basically, it has a factor of the square root of -1, not that you need to know that, okay? Let's go ahead and simplify each of these examples for the next 3, and starting with the square root of 16. So what I like to do when I take a square root of a perfect square number is, in showing my work, I like to rewrite that radicand, that's the technical term for the thing inside of the radical, which in this case is 16, is something squared. And if I could do that, then the square root and the squaring essentially cancel each other out. They're inverse operations of one another. And what gets to come out is the radicand that's left, or the number that's left when you cancel out the square root and the squaring. Now, that was a principal square root, right? Now, you could have a negative square root, which is what we see in number 2 right here. So we can rewrite that. And it's okay to have negative signs outside of your square root all day long. That's actually perfectly fine. Sorry, let me actually erase that. And 36 happens to be a perfect square number. It's 6 squared. So I am going to be able to do that canceling out like I did in the previous one. Boop, boop, right? So we are left with 6, but don't forget, it is negative. So it's like that negative sign is just kind of outside waiting. Waiting in the wings to be affixed to whatever settles out of this simplification here, recognizing the square root and the squaring cancel each other out, okay? Now this one over here, I'm already on that teal color. This one we're gonna look at with a critical eye and be like, oh, look at this, Biz. Under the radical, I have a negative number, okay? So that means that the square root of this particular guy right here is not real. And you could just leave it at that. You'll just say not a real number and move on with your life, okay? Because like I said, we do not deal with stuff in the imaginary number realm. We're just not going to do it. So we'll move on. In this next example, we want to practice using our calculator. Okay, so I just realized that I forgot to get my TI-84 Plus that the math lab was generous enough to lend me in regard to instructing you on how to use your particular calculators. I left it in my office at SMC, and we're not allowed to just go to our office and pick stuff up willy-nilly. We have to make appointments ahead of time. It's like this whole thing because they have to clean the entire building, disinfect it after anyone sets foot in it. They have like really super strict rules about it, which is good. It keeps us all safe. But the bummer is that they don't have specific instructions about like how you make sure that your syntax is correct in putting in this number. So I'll just go ahead and kind of describe to you from off the top of my head how I recall putting this in. I recommend that you start with the square root symbol, which I could not tell you where that is. I believe it's a second function on the squared. the squared function there. Okay, so let's go ahead and practice typing this in, and I'll tell you what value you should expect to get rounding to the second decimal place. We'll just go as far as we can with this together. So if I am doing this, I am taking 0.32. Now I'm doing this on my phone calculator, which is terrible. You shouldn't do it this way. Here we go. And then I'm multiplying it by, and I'm using some parentheses, 1 minus 0.32, and close the parentheses. Okay, and then we divide that by, ooh, I didn't say to do anything. Okay, so anyway, hold up. Let's start with the 1 minus 0.32. That part, I get 0.68, and then I'm going to multiply that by 0.32, and I get 0.2176. Let's divide that by 235, and then I'm going to take the square root of that number. So that's what you do if you're doing it on your cell phone, which I totally think you should not do. If you're doing it on a TI-83 Plus or TI-84 Plus, you should do the square root symbol, and then inside of it, make sure that you are using parentheses appropriately. So I would actually put parentheses down first, then 0.32, another set of left parentheses, right? And then 1 minus 0.32, close the inner set of parentheses, and then close the outer set. And then the division symbol, which looks like a slashy, and then put your 235 in there. Then make sure that all of that is still under the radical symbol, and you should be able to press enter and get 0.0304295. It depends, I'm not sure how long your decimal will go, but I'm going to write all of the decimal places that I see in my particular iPhone calculator. But we're going to round to the second decimal place, it says. So that's here. Check in with the neighbor, and the neighbor's a 0. So then you should get an answer of this as far as what you report for that particular problem. Okay, so let's talk more about how to use your calculator properly to get this answer when we come together for lecture. Okay, that could be a good problem that we talk about in class. All right, let's tackle scientific notation. Okay. Okay, yeah, we're doing good on time. A number written in the form of a times 10 to the n power. Okay, where a has to be greater than but equal to 1 and strictly less than 10. So basically a's value, the ones place value has to, or the place sum to the right of the decimal has to go just to the ones place. So you can't have a tenths place, right? You can't have 10.4 as your a value. It's got to be something strictly less than 10. N is an integer. It could be positive, it could be negative. If it's negative, we have a small number, right? And decimal moves to the left by n places. And if n is positive, right, then we have a large number. That's the most important conceptual thing that I can highlight here. So let's go ahead and just dive into some examples in which we do some conversion. So in the next 3 examples, we have values that are in scientific notation, and it's our job to put them in decimal form, or it's also called standard form sometimes. Okay, so here's the process that I use for this. I will go ahead and just rewrite the a value, which in this case is 6.2, and recognize that my decimal goes to the 7th power, positive 7 that is, which if you go back up to the procedure, if it's positive, you have a large number and decimal moves to the right. How many places? 7 places. The exponent tells you how many places and in which direction to move. Because it's positive, we'll move to the right. Because it's a 7, we'll move 7 spots. So I'm going to go ahead and in this light green color, move 7 spots. So that'll be 1 spot accounting for the 2, 3, 4, 5, 6, 7. So here's the new decimal place location. And like I said earlier, these little waves indicating how many spots I've moved, that is very much looking to me like an empty egg carton. So let's fill it up with some eggs. And by that I mean zeros. All right, once the egg carton is full, then you essentially have your new number in decimal form. And so it'll be, I'll rewrite it because this is just my work shown, but my final answer is actually 6, 2, and then it looks like 5 zeros after that. Every 3 zeros starting from all the way to the right warrants a comma to indicate that you're entering the next period of the number. Like for instance, after this first comma, you're in the thousands period, and then you're in the millions period after the second comma. In any event, we are good to go on that problem. Conversion done. Okay. Moving on to number 3, we have a little bit of a different notation. I'm glad that we have an example like this so you can know what this fancy E is supposed to mean. It's basically supposed to replace the notation of the multiplication symbol x and 10, in which the number after the E, in this case 5, is the exponent on the 10. So this is the same as 3, oops, sorry, let me just rewrite that 3 a little bit better. 3.24 times 10 to the 5th power. Okay, so this E notation is just trying to, be even a little bit more concise than scientific notation, the original version, which was already, the reason we have scientific notation is to make large or small numbers more concise, and this is making it even more concise than that. Okay, great. So let's go ahead and take 3.24 and move that decimal place 5 units to the right. And why am I going 5 units to the right and not to the left? Because this 5 value is positive. So it's 1, 2, 3, 4, 5. Okay, so here's the location of the decimal place now, and I need to put 3 eggs in the carton, and so then the answer, or sorry, the converted value is 324,000. Put a comma right there, and you're set. You are done. So I'll go ahead and, I don't know, box that up like this. Okay. Now this next one can be a little tricky because not only is the A value negative, okay, but so is the exponent. The exponent being negative just means that you move the decimal place to the left rather than to the right. And the value A being negative has no bearing on how many places you move the decimal or in what direction. You're always going to be looking at the exponent for that information, the exponent on the 10, that is. Okay, so go ahead and give yourself the A value, negative 2.3526, and move that decimal place 3 units, 1, 2, 3, but this time, right, to the left. So then egg goes in here. I know, don't forget that this number still stays negative. And go ahead and also put an egg, or rather a 0, in front of the decimal place. That's just a little bit of convention there. I know you might be thinking, what if I don't like to put zeros in front of decimals? Well, that's your stylistic choice. I really don't care that much either way, but you might have instructors in your future that really care about that kind of stuff. So just be warned that this 0 in front of the decimal place for numbers that are less than, less than 1. And it needs to be negative. Let's not forget that. That is a convention upheld by mathematicians all over the place, and yeah, instructors usually go for that. Okay, great. So notice that I've just rewritten the problem, and I remembered, thank goodness, that it was still negative, and I just put all the eggs in the carton and 1 egg out in front as well. And so this number, because it has 1, 2, 3, 4, 5, 6, 7 places after the decimal, it's actually the name of this number would be negative 23,526 10 millionths. What a fun name for that number. It just sounds so tiny. Yup. Teeny, 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 tiny number. Let me go ahead and box that up in yellow for fun. Okay, great. Now let's go the other direction with it. Let's take these numbers that are in standard form and let's write them in scientific notation. So it's your job to determine what the appropriate location is for the decimal in order to turn this large number into a number between 1 and 10. Inclusive on the 1, exclusive on the 10. So it looks like, if you can see where my cursor is hovering, it looks like I want to put my decimal right between the 2 and the 5. So that way it'll become 2.501, and those 2 zeros after the 1 I could just leave off at the decimal, okay? So here we go, 2.501, and I got to multiply it by 10 to the what power? Well, how many decimal places did I move in order to have the decimal place, which was originally in this position, move to that position? Well, let's count them, and we'll count it on top because I already have some stuff written down below here. So that's 1 spot, right? 2 spots, 3, 4, 5. So it's a positive 5, the exponent on the 10. Why is it positive instead of negative? I moved to the left. It seems like that's always associated with negative exponents, but hold on, we're going in the opposite direction as far as the process is concerned, so it should be kind of counterintuitive and backwards. The rule of thumb is, if you're converting to scientific notation, which is exactly what we're doing in this example, your exponent is going to be positive if the original number was relatively large, which is what we have in example 1, and it'll be negative if your original number was relatively small, like we have in example 2. So moving on to example 2, go ahead and determine where this decimal should move in order to turn this super duper small and also negative number, but that's not part of the process here, it just happens to be negative. Where does this decimal need to move in order to turn this number into a number between 1 and 10? Well, it's got to move right here between the 6 and the 5, right? So how many places does it need to move? 1, 2, 3, 4, 5, 6 places. But, you know, we're going from, we're starting off with a real small number, so the negative 6.5 will be multiplied by a 10 to the negative 6 power, okay? So hopefully that all makes sense and feels good for everybody. Let me know if you have any questions about this or want to see more examples about converting to and from scientific notation. All right, moving on. We've got some percentage increase, percentage decrease problems. So fun. All right, and very tricky, okay? So don't feel bad if when you work on these things in homework the first time or two, it's, you know, it might require a little bit of struggle to get through, but don't worry, you will get it with enough practice. And remember the things that we're going to write in this first little box here. This is the trick. So let some quantity change by percent p occur, right? So it increases, for percent increases, that is, if you see this phrase increased or whatever and there's a percentage, you want to multiply by 1 plus the decimal representation of the percentage. So for example, if we say that some price increased by 25%, you would multiply the original price by 1.25, right? Because that would be 1 plus 0.25, the decimal representation of 25%. Okay, now if you have a percent decrease, you will multiply by 1 minus the decimal representation of the percentage. Okay, so let's go ahead and have a couple of examples in which we use this rule here. Starting with number 1, a company's sales were $52.8 million in 2014. The sales total increased by 22% in 2015. What was the total sales in 2015? Round to the nearest $1 million. Okay, so we should take 2014's company sales and multiply it by what in order to find the 22% increased total sales. Okay, so go ahead and keep this as a decimal because we have our value that we want to calculate rounded to the nearest $1 million, so that's the unit. 52.8 therefore should be multiplied by, since it's an increase, we will let this be 1 plus, what's the decimal representation of 22%? It's 0.22, right? So 1 plus 0.22 is 1.22. So that's how I'm getting the multiplier that I'm about to impose on this $52.8 million. Reach for your calculator. Multiply those values, and what do you get? 52.8 times 1.22, and I get 64.416. Now, that's more information than I need, but I think it's good in my work to write down the entirety of any decimal value that I get in my calculation. Like my calculator did all the work. What I can do to make sure that I have a high amount of accuracy with my final answer is to write down the entirety of whatever my calculator gave me, and then in a separate step do the rounding. So I'll make it in another color. We're going to round to the nearest million, so that's the nearest whole number. Since the first decimal place after the value that I'm trying to round to is a 4, we're just going to cap it off at 64. So in this regard, we should have our final answer written in a full sentence. And it should say the total sales in 2015 was about, and you could say about because we are rounding, $64 million, which would look like that. Okay, cool. Let's do one more, and then we'll be done with this lecture video. The revenue of a newspaper was $32.5 billion in 2000. It decreased by 3.8% in 2001. What was the total sales in 2001? Round to the nearest $1 billion. Okay, so keep that in mind. Go ahead and make this conversion happen. It'll be 0.038 as a decimal. That's 3.8% as a decimal, not 0.38. That would be 38%. So be careful when you're doing this conversion. And then we need to, because it was said to be decreased, take 1 minus 0.038. And what does that get you? Well, you might actually reach for your calculator for this, or put it down by hand, because it's not as easy as just adding, right? Cool, so this will give you a multiplier of 0.962, okay? Now let's go ahead and multiply that by the 32.5 billion, which was the revenue in the previous year, because when you're talking about it increasing and decreasing from year to year, you always have to base the calculation on what happened the previous year. So if we need total sales in 2001, which is what they're asking us, we need total sales in 2000 multiplied by the appropriate multiplier, which we just calculated here, of 0.962. And what do we get when we multiply those numbers? We get 31.265. We are indeed going to round to the nearest $1 billion, so let me go ahead and get another color out here, right? Again, we'll just keep it at 31 then, because the neighbor to the rounded value was 4 or less. Well, 2 is definitely less than 4, so we're good on that one. And let's go ahead and write our concluding sentence. The total sales in 2001 was about $31 billion. And there you have it. Okay, that concludes our lecture video covering the entirety of 1.6 and 1.7 sections for Math 50, so we can have an ample discussion in class, and then also be prepared to do some in-class worksheets with some small groups that I come up with randomly. Very good. Thanks for your attention, guys.